And in today's class we're going to learn about the behavior of conjugate acids and bases. A conjugate acid, we'll recall, is the acid that results when a base is protonated, and a conjugate base is, for example, the acetate anion, which results when acetic acid gives up its proton. And it's called the conjugate base because the acetate anion does have basic properties. And if you don't believe me, you can try eating a bag of salt and vinegar chips and look at what happens to the inside of your mouth the day after. The acetate anion is corrosive enough so that the lining of your mouth turns white and a lot of the skin cells will fall off. So this is one proof where we can have personal experience. It's not highly corrosive, so obviously it wouldn't be found in food if it was dangerously corrosive, but it is corrosive. So we're going to explore this possibility of affecting the pH with a conjugate base of a weak acid. Acetic acid is a weak acid. It'll donate a proton to water to generate the hydronium ion and the acetate anion. Likewise, if you were to take, then here I've just represented the same thing, having factored out the water. Typically when they record Ka values, the concentration of water is included in the Ka value because the concentration of water in aqueous solution usually hovers around 55 moles per liter. And it would be just cumbersome to have to deal with it mathematically at every calculation. So they've incorporated into the value of Ka. That's why we can write it this way, and it's equivalent. We're just showing the acetic acid dissociating into the acetate ion and a proton. Likewise, if I were to take sodium acetate and put it in water, the acetate anion would abstract the proton from the water molecule and generate hydroxide anion, and then regenerate acetic acid. This is also an equilibrium process, basically this one flipped around, and you could represent it as acetate generating acetic acid plus hydroxide, and we call that Kb. When you place the product over reactants, you could portray it as the concentration of acetic acid times the concentration of hydroxide anion over the concentration of the acetate anion. And to find out what the Kb value is, all we need to know is the Ka value, unless it's reported directly. The Ka times the Kb always equals Kw. Kw equals 1.0 times 10 to the minus 14. That comes from the autoionization of water, which is a spontaneous process. Water will break down into hydroxide and protons at a very small rate, but nevertheless a measurable rate, which when multiplied gives you, when you multiply the concentrations of hydroxide and protons in water, you get 1.0 times 10 to the minus 14. So we use this number to also calculate the value of Kb for conjugate bases. The Ka value for acetic acid is 1.8 times 10 to the minus 5, whereas the Kw for water is 1.0 times 10 to the negative 14. So if you take Kw and divide it by Ka, you'll get the value of Kb. Just throw that in as a reference. So the value for Kb for the acetate anion is 5.5 recurring times 10 to the minus 10. We can work out a question where we are asked what the resulting pH is if we dissolve some acetate anion into an aqueous solution. So we were asked, what is the pH of a solution with 30.2 grams of sodium acetate dissolved in 1 liter of water? So the first thing to do is find how much sodium acetate is present. We divide by the molar mass of sodium acetate. Here is the mass of sodium, mass of 2 carbon atoms, 3 hydrogens, and the 2 oxygens. So it turns out to be 82 grams per mole. There's 30 grams, so we have less than 1 mole of acetate anion in solution, 0.368 to be exact. We set up an ice table showing, first of all, the chemistry. The acetate ion combines with water, giving you acetic acid and hydroxide ion. We're not going to count water in the equilibrium expression. 0.36 minus X amount dissolves to give you an equilibrium value of 0.36 minus X. Acetate ion forms in the same amount, X forms, and at equilibrium you have X concentration of it, and same with hydroxide. So we set up the equation 5.5 times 10 to the minus 5 is equal to X squared products over reactants. And then I make the assumption that the value of x is going to be so tiny that it hardly puts a dent in 0.36. When we do the calculation, we find that x is equal to 1.43 times 10 to the minus 5, which is essentially 4 orders of magnitude lower than 0.36, which means my original approximation was correct. But just to satisfy our curiosity, I took this number and I plugged it back into this equation. So that I took 0.36 minus this amount, so I give it more, I iterated once. And the result was hardly different from the first. We had 1.4301. After iterating one time, we got 1.43008, which is almost the same as 1. So iteration is not going to help us here because we're already very close to the correct value with the approximation. So there's no need, there's no appreciable change, so we're not going to continue the iterative calculation. We use this number to find the POH. Remember that POH is equal to negative log of OH minus concentration, and X represents OH minus concentration. So we get a value of POH of 4.8. You have to be careful at this juncture that you don't forget that what you have is a POH. If the question in an exam asks you for a pH and you report a POH, you're going to get the wrong answer. You have to do one more step. pH plus POH equals 14. You subtract 4.8 from the 14 and you get the pH is equal to 9.16. So we can conclude by saying that the conjugate bases of weak acids are also weak bases, and that the conjugate acids of weak bases are weak acids. However, we should recall that the conjugate bases of strong acids do not have any appreciable basicity, and that the conjugate acid of strong bases do not have any appreciable acidity. An example, hydrochloric acid, which is a strong acid, will combine with water to give you the chloride anion and the hydronium ion. Chloride does not affect pH. If you took sodium chloride, which is the product of the salt of a strong acid and a strong base, it has no effect on pH. pH of a salt solution is going to be very close to 7. On question 16.87, they ask us about to estimate which one of these salts is going to have the most basic solution. And they give you sodium chloride, sodium hypochlorite. Right off the bat, you can state that sodium chloride is going to have no effect on the pH. So the contest is between sodium chloride and sodium hypochlorite. And the textbook doesn't report a Kb value for fluoride anion or the hypochlorite anion. However, it does report Ka values for hydrofluoric acid and hypochlorous acid. The Ka for hydrofluoric acid is 6.8 times 10 to the minus 4. So if we plug that into Kw over Ka, we get that Kb for fluoride anion is 1.47 times 10 to the minus 11. Likewise, for hypochlorite, the Kb value is 3.3 times 10 to the minus 7. So the stronger base of the two is the hypochlorite anion. It's got a bigger number for Kb, the Kb value. So the more basic of the two is the hypochlorite anion.